Hey everybody! So, welcome back. In the past few videos, we've talked about exponential functions, logarithmic functions, and compound interest. Essentially, some of the more algebraic applications of exponential and logarithmic functions. But this is a calculus class, so we should probably talk about, well, how do you actually take a derivative of the exponential function? So here's the rule, which I will not prove. Proof requires something known as L'Hopital's rule, which we have not covered in this class. Proof states that the derivative with respect to x of e to the x is, in fact, e to the x again. How about that? So, nice little one, right? In other words, the natural exponential function f of x equals e to the x is the unique up to scalar multiple function such that f prime of x is equal to f of x, right? If you let f of x equal e to the x, the derivative is equal to the original function. This would also be true for any scalar multiple of e to the x, right? Because scalars pull out of the derivative. So if you took the derivative of 2e to the x, you would get 2 times derivative of e to the x, which gives you back 2e to the x. Alright, so that's cool. It's a nice little differential equation that gets solved there. This actually was the function that motivated the study of what's known as differential equations. But yeah, so let's take this rule, use it kind of in conjunction with some of the other stuff we've talked about, like the product and quotient rule and the chain rule. Let's say we want to compute the second derivative of f of x equal to x cubed e to the x. Alright? So by the product rule, f prime of x is going to equal first times derivative of the second plus second times derivative of the first, which is equal to x cubed e to the x plus 3x squared e to the x. If you fancy, you can factor and you would get x squared times x e to the x plus 3, or sorry, x squared e to the x times x plus 3. I'll accept either one of those forms. This one's probably more clear that we just used the product rule. But now we want the second derivative. So, not this. We want f double prime of x. And let's work with it from here. So we need to take the derivative of this, and that'll give us, okay, we're going to have 2 product rules that happen. So we're going to have x cubed derivative with respect to x of e to the x plus e to the x derivative with respect to x of x cubed. Funny, it's almost like we're getting the first derivative back in there. Wonder how that's related to the exponential function. Plus, okay, now product rule right here says first times derivative of the second plus second times derivative of the first. And I'll give you x cubed e to the x plus 3x squared e to the x from here, plus another 3x squared e to the x, plus 6x e to the x. So you can write that as x cubed e to the x plus 6x squared e to the x plus 6x e to the x. And if you wanted to, you could factor out from all that, just kind of like what we did up here. But this would be our second derivative. So, computing derivatives involving the exponential function, pretty nice, right? And it gets these kind of interesting recursive patterns where we see, hey, this thing that popped up when we took the first derivative pops up again in the second one. That's just the nature of the exponential function. Let's do another example using just plain exponential function. Let's let h of t equal e to the t minus 1 to the 5 halves power, and we want to compute h prime of t. Okay, so examining this, we see there's a pretty clear inside and outside portion, which means, hey, we probably have a setup that would use the chain rule. So, what are we going to do? We're going to let u equal e to the t minus 1 and y equal h of t, which in this case would be u to the 5 halves power. Then, h prime of t, by definition, will be dy dt, right? We're talking about a function of t, so we're taking dy dt. Chain rule says that's equal to dy du times du dt. Okay, what are those two derivatives? Well, dy du is going to be 5 halves u to 3 halves, and du dt, well, derivative of e to the t is just e to the t, derivative of 1 goes away, so we're left with just e to the t. So we'll have 5 halves e to the t times e to the t minus 1 to 3 halves power if we substitute back in our definition for u and just put it out on the other side. Alright, so that's the derivative of just the plain exponential function, but I could put e to the other things than just a single variable, right? What if I put something like e to the x squared? Thankfully, the chain rule tells us how to deal with that too. Alright, so the chain rule says that the derivative with respect to x of e to the f of x, where f of x is some arbitrary function that we don't know, is going to be equal to e to the f of x times f prime of x. You can put f prime in front if you want, doesn't matter. Typically, you will, just because it's typical to put exponentials at the end of the expression, for whatever reason. Anyways, that's a notational thing. So, why is that? Let's do it out with a little more detail. If we let u equal f of x and y equal e to the f of x, then by the chain rule, derivative with respect to x of e to the f of x is dy dx, right? Since we've set y up to be that thing, which is dy du times du dx. Okay? So, e to the f of x is also equal to e to the u. So now, dy du is just e to the u. Derivative of e to the u with respect to u is e to the u. Then du dx, well, we don't know what the derivative of f of x is. So just write it as f prime of x. Who cares? And then substituting back in for u, that's e to the f of x times f prime of x. Exactly as we wanted. So, in general, this is the formula. To take the derivative of e to whatever function you want, you take the derivative of the function up top, and then you multiply it by your original thing. Pretty nice. Let's do a couple examples with it. So let's say we compute the following derivatives. First, let's say e to the x squared. Next, e to the 2x minus 1. And finally, let's say g of x is equal to e to the negative 2x cubed. So you should try these on your own first, and then, so pause the video, try them, come back. Alright, hopefully you have some trial solutions for these, and let's do them together. So for part A, by the thing we've developed up here, f prime of x will equal, please note, this f prime of x is not the same as this f prime of x. We're using x squared as the f of x here. So notation is not great, but that's not that big of an issue. So f prime of x will equal e to the x squared times the derivative with respect to x of x squared, which will be 2x e to the x squared. Nice and simple. Now for part B, well, f prime of x will equal e to the 2x minus 1 times the derivative with respect to x of 2x minus 1. Derivative of this thing is just 2, so this will give us 2e to the 2x minus 1. And finally, g prime of x will be e to the negative 2x cubed times the derivative with respect to x of negative 2x cubed, which will give us, that'll be a negative 6x squared, so that just gets multiplied in front. Negative 6x squared e to the negative 2x cubed. There we go. Ta-da! So, applying the chain rule with the exponential function is nice and simple. Simple enough you don't really even need to write it out most of the time. Alright, let's move along. Your book doesn't cover this, but I think it is probably a natural question to ask. This is the natural exponential function e to the x, and how to take derivatives there. But what about other bases, like 2 to the x, 3 to the x power? I would very much like to know how to take the derivative of those too, please. So, let's figure out what that should be. Alright, so what is the derivative of a to the x for any a greater than 0? This actually does still hold with 1. I know that was the special case when we defined the exponential function, but this formula will still hold. Okay, well, let's just start playing around with stuff. seeing what we can get. I know how to take the derivative of e to the anything. So is there a way I can somehow switch a to be in terms of e? Well, remember, by just standard properties of logarithms, a is equal to e to the natural log of a, right? E and natural log are inverses, they cancel out. So we have that equality. Let's just try plugging that in to this equation right here. This is the derivative with respect to x of e to the natural log of a to the x power. But now properties of exponents say you can rewrite that as being this exponent times that exponent. X times the natural log of a. And we know how to take this derivative by the chain rule, right? The thing we've already done. This is going to be e to the x natural log of a times the derivative with respect to x of x natural log of a. Natural log of a is just some number, right? So we have some number times x, the derivative of that is the number. So we're left with e to the x natural log of a times the natural log of a. But e to the x natural log of a was exactly a to the x. So the derivative with respect to x of a to the x is a to the x times the natural log of x. It's almost like this natural log of a is the conversion fee you pay for working in base a instead of in base e. That's another reason that e is the natural exponential function, is because the natural log of e is just 1, right? So you're just left with e to the x plain. Nice and simple, but still kind of a neat trick, right? This little rewriting thing is very helpful whenever you try to prove things involving exponential functions of different bases, since most of the time we know how e works better than we know how all the other ones do. Alright, so let's use this, do a couple examples, and then I think that's it for this video. So let's find the derivative of g of t equal to 2 to the t power divided by 2 to the t plus 2 to the negative t power. Alright, I hate to say this, but it looks like we're going to have to use the quotient rule. It's a sad day for us all. Is there a way to get around it? Nah, not easily. Alright, let's just do it with the quotient rule. G prime of t by the quotient rule will be bottom times the derivative of the top minus the top times the derivative of the bottom. Just put that on in there. Divided by the bottom squared. Alright, computing this first derivative, here a is 2, so we're going to get back 2 to the t times the natural log of 2. So we have 2 to the t plus 2 to the negative t times 2 to the t natural log of 2, and then I'll put this on its own line, minus 2 to the t times, okay, So for 2 to the positive t, we're going to get another to the t natural log of 2, right, from that half of the derivative. And then from this half of the derivative, just like with the exponential function, how that changed, and you said, oh, you just multiply by the derivative of the other. Same thing here, right? Derivative with respect to x of a to the f of x will be a to the x natural log of a times the derivative of whatever's in the top, for the exact same reason as it is for the exponential function. So here, since we have a minus sign on this 2 to the negative t, when we take the derivative, it just translates to a minus sign in the front. So minus 2 to the negative t natural log of 2. All divided by that being squared. Alright? Well, let's use our exponential rules and start simplifying things. As soon as I pick up an eraser or two. Alright, so from here, exponential laws say, okay, this will be natural log of 2 times 2 to the 2t, 2 to the t times 2 to the t, 2 to the t plus t, aka 2 to the 2t. And then 2 to the t times 2 to the negative t is just 1. Okay? And then how about over here? Again, we have a natural log of 2 in both factors. So we're going to have minus natural log of 2 times 2 to the 2t minus 2 to the negative t times 2 to the t is 1. Divided by, okay, let's do the actual squaring. We're going to have 2 to the t times 2 to the t, that's 2 to the 2t. Then we're going to have a 2 to the negative t times 2 to the negative t, that's plus 2 to the negative 2t. And then what about the middle terms? Where we're going to have 2 of 2 to the 2t times 2 to the negative t. It's a lot of 2's to the blank flying around. But anyways, these two are going to multiply together twice. And that's going to give us 1 each time. We're going to have plus 2. Fancy little thing right there. I don't know if expanding that was helpful or not. We'll find out. Worst case scenario, we put it right back. Okay, let's simplify. We have a natural log of 2 times 2 to the 2t, and we have a negative natural log of 2 times 2 to the 2t. So those cancel. Those will cancel each other with the natural logs of 2, of course. Right, they have the same factor in front. Then we have plus natural log of 2 minus negative natural log of 2. So plus another natural log of 2. So we have plus 2 natural log of 2. Divided by 2 to the 2t plus 2 plus 2 to the negative 2t. You can work around with this a little more if you wanted. You could divide everything by 2 and you get 2 to the 2t minus 1, yada yada yada. I'll leave it like this. Pretty slick if you ask me. Let's do one more example. Using some of our chapter 4 stuff for this. Let's find the inflection points of f of x equal e to the negative x cubed. You know what? For the sake of it, let's make it 2 times e to the negative x cubed. Getting spicy here. Alright, so let's remember, an inflection point is a point where the second derivative changes sign. Concavity changes sign. It's equivalent to the second derivative. Okay, so let's find that second derivative and see where it changes sign. F prime of x will equal dx of 2e to the negative x cubed. 2 pulls out in the front, and we're just going to be left with 2e to the negative x cubed derivative with respect to x of negative x cubed. So negative 2x cubed. Derivative of negative x cubed is negative 3x squared. So we'll be left with negative 6 e to the 6x squared e to the negative x cubed. Alright, that's our first derivative. Now we have to take our second derivative. I see that here I'm going to have to use the product rule. Oh well. F double prime of x will be first times derivative of the second plus the second times the derivative of the first. Derivative of this thing, just like up here, will give us, instead of that, it's the same as this derivative, this first derivative, except we don't have a factor of 2. So it'll just give us negative 3x squared. E to the negative x cubed plus e to the negative x cubed times negative 12x. Multiply everything all together and you get 18x to the 4th power e to the negative x cubed minus 12x e to the negative x cubed. So that's our second derivative, and now what we need to do is we need to find inflection points. How do we do that? We set it equal to 0 and we divide up the real number line. Alternatively, we find points where the second derivative is undefined. Let's think about it. Does this ever have a chance of being undefined? Well, we do have a division going on, right? E to the negative x cubed, that's divided by e to the x cubed. But the range of e to the x is strictly positive, right? E to the x looks like this. So it never hits 0. We never run into a problem. It'll never be undefined. So let's just solve f double prime of x equals 0. Alright, so if 0 is equal to 18x to the 4th e to the negative x cubed minus 12x e to the negative x cubed, let's multiply both sides by e to the x cubed just to get rid of the negative x cubes right here. And we'll get 0 is equal to 18x to the 4th minus 12x. Why can we do that? Because this is never 0. Alternatively, what we do is we could factor it. That might be better. We have here 6x times 6x e to the negative x cubed times, from this half, 3x cubed minus 2. Is that right? Yes, it is. How about that? Alright, so now we just check where each of our factors are 0. This part, never 0, no matter what x is. Right? It's e to the thing, never 0. This part is equal to 0 at 0. We also have the chance that 0 is equal to 3x cubed minus 2. That's the only other place a 0 could be by a factor. Which means 2 is equal to 3x cubed, 2/3 equals x cubed, so x is the cube root of 2/3. Alright, let's split up our number line and go from there. Putting these 2 points on the number line, we have 0, and then cube root of 2/3. Well, this is a positive number. I'm taking the cube root, so I'm going to get another positive number. No need for decimals here. Now we just need to pick some test points. Okay, well, maybe -1 is kind of an obvious test point on this side of 0. And over here, 2/3 is smaller than 1, meaning its cube root is smaller than 1. So maybe 1 is a good test point right here. The only question is, okay, what should our test point be here in the middle? I don't know, maybe the cube root of 1/3? I don't know if that's a good choice, but I know for sure it fits in this interval, and I don't feel like busting out a calculator. So, let's do it. Hopefully it'll work, and I think it will. Okay, if we check f double prime of x at each of those test points, f double prime of -1 is, let's see here, plugging it in to this, or to that, either or. 18 times -1 to the 4th power times e to the -1 cubed minus 12 times -1 e to the -1 cubed. That's equal to 18. -1 cubed is -1. -1 is just 1. So we're going to be left with 18e plus 12e. So you're going to be left over with 30e, which is a positive number. Alright? Let's also check 1 first, just because that's probably easier. Very similar, except for that sign will change and those signs will change. So we have an 18 e to the -1 minus 12 e to the -1. Alright, so we're left with 6 divided by e. Still greater than 0. E is positive, 6 is positive, whole thing is positive. Alright, now it remains to check at the cube root of 1/3. F double prime of the cube root of 1/3 will be 18 times the cube root of 1/3 to the 4th power e to the negative cube root of 1/3 cubed minus 12 times the cube root of 1/3 to the 4th, or sorry, just cube root of 1/3, e to the negative cube root of 1/3 cubed. Alright? I don't really know what the cube root of 1/3 is, so I'll factor it out. This is the cube root of 1/3 times 18 cube root of 1/3 cubed, right? I'm just trying to get it away from this one. Cube root of 1/3 cubed, and the reason that's helpful, because now we'll have a cube and cube root that can cancel. E to the negative cube root of 1/3 cubed minus 12 e to the negative cube root of 1/3 cubed. And now our numbers simplify very nicely. Well, the cube root of 1/3 times cube root of 1/3 cubed is just 1/3. 1/3 times 18 is 6. E to the negative 1/3 minus 12. E to the negative 1/3. So we'll be left with negative 6 cube root of 1/3 divided by e to the 1/3. 6 minus 12 is negative 6, everything else is just multiplying out. Negative times positive is negative, divided by positive is still negative. So we see that the sign of the second derivative goes from positive to negative to positive again, which means that we have inflection points here and here. I'm going to erase this. Hopefully y'all got that. Basically all we did was we showed that this thing was less than 0. Yes, you could do that by plugging it into a calculator, but I don't own one. I mean, I have my phone, but okay. So f of x has inflection points at x is equal to 0 and x is equal to the cube root of 2/3, since the second derivative changed sign as we passed over. Alright, I reckon that's everything for this video. Have a great rest of your day.